Uh, Before we start to talk something about the ensemble learning, so any question else beside this topic? Because last time I just see there are some problems with regression, right?
Yes.
I mean, I mean that maybe last time when we have the weekly like presentation, some guys just mentioned that the Ghani group make some problems with regression. Is is this problem solved already?
No, actually, I think what we are having a problem is not for running the code, but after the result, what we are getting, I think that result is not showing very like the result is not satisfactory. We want better results, so it's not running the code, but the output.
Oh, cool. I cannot hear clearly. So if if you can type it and if you have questions.
Yeah, I type it.
Chang, I think you can start to talk about the your presentation, and we can discuss later.
Okay, great. So today we will just have a second meeting or on the second part of the example learning because just as we know, the last lecture we just learned something about the voting, bagging, and parsing, and which just lead us to the final algorithm we want, the random forest. And we just have an example on the decision tree because we take this algorithm decision tree as a base model to train. And this is the first way, and we can call it the first type of the example learning because as this picture shows us, when we are using the bagging, actually all the predictors are trained parallelly, which means that or they are not connected closely when we are train them. So we can train them all together. And this is why we call it the first type. And today we are focusing on the second type, and which will just lead us to the final algorithm we want, like the charge boost and like GBM. But we don't shed a lot of attention on this algorithm itself. And when we are going to use it, and we can have another meeting to talk some like the mathematics knowledges behind it. And today we just focus on the source of this or on the source of this kind of example learning method. And we call it boosting. And also we will just have another talk with there's the other methods. We can call it stacking. And usually when we are talking about example learning, actually we are just want to take advantage of the wisdom of the crowd because we just aggregate all the weak estimators and we are build up a stronger estimators to get better results. And those kind of like the results we get are we aggregated or is bound to be it's bound to be working well than an individual one. So this is the insights of the example learning methods. So literally, it is just an aggregated predictor, but we have various ways to do this job. So today we will just focusing on the boosting and stacking. And in fact, what is the boosting? When we are talking boosting, it means that we just train the predictors sequentially. And every time when we are just trying to train them, it is just to correct its prediction. And so, which means that it can't be trained parallelly. like this picture show. As this model will be trained, and then the successor will train on the result by the predecessor. And we'll start with the first common approach of boosting. We call it ad boost, and which is short for adaptive boosting. So what is adaptive boosting? And on the left side, here is the code of the real application of the ad boost. And on the right side, we can see some logic under the hoods. And all the code, I will just put them on the GitHub because they are optimized these days. And the targets of the ad boost is just to focusing on the training instances, because maybe this kind of training instances their patterns are ignored by their predictions. So we will just train a series of predictors on the same training data set. But what's the difference between the ad boost and like the bagging? And we can see later. As this picture shows us, if we have the training set like this, and then we use the first predictor to train on this data set, but actually we can see that it is not perfect enough to just simulate the patterns of the training data set. So it is unavoidable that the score will not be as perfect as we want. So which means there are some training instances who may be underfitted. So in this way, we just increase the related weight of the misclassified like the training instances. And then, as you can see, for the first predictors, it can just draw a line to just partial maybe these groups of the data set, but there is one data it cannot just connect, and then we will just increase the relative weight of this instance, and just sequentially we use the second predictor to train on this training set. But the difference between this training set and this one is that the relative weight of the singular or of the single instance is different, because we use a math formula to calculate the relative weights, and then we use the second predictor to train on the same training data sets with various relative weight of each instance. And the process will just repeat it again and again until we have all the predictors trained enough. And this is the training steps when we are using the adaptive boosting. And how can it work? Like, actually, the first step for the adaptive boosting, it is just to calculate the weighted error rate of the predictor. As you can see, the J here means the J predictors saw in the picture. We can see the first predictor like this, and the second predictor, the third and the fourth one. And it will just calculate the weighted error rate. And actually, in the very first beginning, all the instant weight will be just to set initially to 1/n. Because from the statistical view, every instance has the same equal weight at the very first beginning, because we just don't know what instance will weight more than the others. So initially they will be set to the same value, and it will help us to calculate the initial weighted error rate. And the second one is to just do some measures on the predictor rate, because as we can see, from the view of the crowd, not every person have the same wisdom, and which means that not every person will be the expert. And we usually know that maybe some kind of experts who are good in some grants, their words will just be way more higher than the normal person. So we will just calculate the predictor weight, and we see this weight as how important this predictor contributes to the whole ensemble. And as this formula shows us, it will just calculate the alpha. And here we can see the eta. Eta refers to the learning rate hyperparameter, and it will default to 1. And this is why I just shed some light on it, because as I have emphasized over and over again, the hyperparameters we see on the code, like the left side, we see on the code like this. Actually, it is represented in the formula. So it's not like arbitrary for you. It's not arbitrary for you just to set random values on the hyperparameters. Actually, every hyperparameter has its physical or math meaning. And after you learn something under the hood, and you would know when you are increasing the one specific hyperparameter, and what result will you get later, because they are just originating from some specific math, and you can just make some estimations before you train the model. If you get used to this formula, and then when you are trying to increase this value, and before starting to train, you will have some estimation on it, because you know the learning rate just represents the eta in this formula. And this is why it's important for us to just learn the methodology behind it. And actually, as we can see from the training process, the relative weights of the individual instance will be changed after each iterations. And how can it work? Actually, the formula in the third equation shows us the weight update route will just be as simple or just beyond your imagined. It use this one to just change the instance weight. And the last thing he should do is to do the normalization, because we know the summation of the weight should be 1. So if you change the weight every stage, how can you guarantee the summation, the results of the summation? So for the adaptive boosting, it will just do the normalization after it just updates the individual's weight. And this part would be quite interesting, because we know the connection between the physical world and the math words will just be some simple formulas, and you should just paste, or you just put some times into this kind of formula, and it will help you to grasp the real magic of this algorithm. And at the end, so what result will the AdBoost algorithm give us? It will just compute the prediction of all the predictors. But the difference thing is that it will weight them using the predictor weight alpha. And also the predicted class is the one that received the majority of the weighted votes. And if you just recap what we have in the last meeting, and you will see the wisdom in this adaptive algorithm will be very likely, or will be very similar to the ones when we are talking about bagging and about voting, because on the second pattern of the voting, we talk about like the hard voting and soft voting. So here are some notice we should note. After you learn the AdBoost, the first thing just pop into your mind is that, is it similar to the gradient descent we see when we are setting the loss function? Because they are quite similar. But the difference thing is that the AdBoost just adds the predictors to the ensemble, as we can see a series of predictors, and to make the result better. But for the gradient descent, the way it performs is that it tweaked a single predictor's parameters to minimize the cost function. So this is the difference thing in here. And what is the gradient descent? Like when we are talking about the linear and polynomial regression, and here is just a big part on the docs I put is about the gradient descent. And this is a way for us to just calculate, because we can not get the formal value directly, and we maybe use some other numerical methods to calculate the loss functions results. And when we are using the deep learning, and when we are just talk something about the DNN and other else deep learning algorithms, and it will be very just common for us to this word gradient descent, because when we are talking them, and we're just focusing on this part when we are trying to use the deep learning algorithms. And the second one is that, like we talk about the bagging and parsing, but the difference is that AdBoost algorithm will depend on their overall accuracy on the weighted training set. And after this meeting, you can just read these talks, and it will just get you a subject of this whole algorithm. And as you can see on the left side, the hyperparameter algorithm some are like there's some, and actually it stands for the statewide addictive modeling. And why I put it here, because in these code examples, maybe I just forget it, how many classes I want to predict, because it is a classification job. And at the very first beginning, I just import a data set into this notebook. And actually, when we are doing the binary classification job, we don't need to set this hyperparameter because the default of the adaptive algorithm will work well on the binary classification job. And if we want to solve the multi-classifications, we need to set this hyperparameter because it will use the multi-class exponential laws to deal with the multi-class labels. And when we are setting the dot R, which means that this algorithm will just rely on the class probabilities rather than their predictions. And this is also the theme I just emphasize when we are talking about the voting, because as we can see, in some kind of algorithm like the SVM, there are by default, it is unable to give us the class probabilities. But in some case, when you set the specific hyperparameter, it will work also with some tragic or strategy to perform it. But you should make sure that which one you are going to use, because the class probabilities is distinguishedly different from the prediction results. And so every time when you are going to train your model when using this kind of algorithm, and you should get fully aware of them at the very first beginning. So it's quite easy for us to apply the add boost. It's quite easy for us to apply the add boost or ensemble learning method, because as you can see, you can just import them from this library. And the way will be the same as we see before, like when after such or after 3 just meetings on the machine learning algorithm, I hope that you will see the patterns, the scikit-learn library performs is quite the same. So after you just grasp the patterns of it, and you will know how to perform them perfectly. And here's is the real data set we want to predict. And this picture is an example, because I just import the data sets from the current library, and this is a public data set, and I just want to show the result of the add boost. And also, as we can see, for the tree-based model, commonly it will just give us the feature importance. And this is why we want to just apply the ensemble learning. And this is one of the reason why we want to apply the random forest, because apart from the prediction result, it can give us the more important things. You can see that it can tell us which features in this data set will contribute more to the whole result. And this is the feature importance, or like a feature selection. We call it feature selection. When we are we call it feature selection when we apply the random forest. It can help us to do some selection on the features itself. And when we are using the PCA, PCA is one of the way of the dimensionality reduction, and we call it feature extraction, because we want to reduce the dimensions of the data sets, or we want to reduce that, but at the same time, we want to keep as much information as we can of the data set. So they are different because one is the feature selection and one is the feature extraction. So when we apply the different algorithms, and you should know the difference between them. And here is the feature important result the AdBoost gives us. And there is one thing I hoped we should notice is that, like for the example learning methods, one common way for us is just to take the decision tree as the base model. But is this essential for us to do this? Not actually, because we can use other algorithms. We can, because in like machine learning projects, we don't just use one algorithm to make prediction. Usually we just use a bunch of algorithms to perform the same job and just compare the result of them. So at this time, maybe we can use one of the example learning algorithm, or no, one of the example learning methods to aggregate the results the like different algorithms give us. So this is why we hope after perform some individual algorithms, maybe we can try with some example learning method to get a better result. Because when we are using the deep learning algorithms, literally it is we cannot just describe the patterns it works, because it's like a black box model. But why we can rely on it? Because it can give, or it can guarantee the higher accuracy it will have. So in this way, maybe we can use the example learning method to improve their accuracy. And this is why we use the example learning method here. And also, the example learning algorithm is called the matter algorithm because it works on the algorithm rather than the data set directly. And so this is why we call it matter algorithm. Okay, after learning the adaptive boosting, so any question you have? Because later we'll just move on and we'll just go into the second part of this meeting. So any question on the AdBoost algorithm? Okay, if not, and we'll just go forward. And today, the second example learning methods I want to introduce is gradient boosting. And from the name of this gradient, and maybe you have some maybe you will just want to compare the difference between the gradient boosting and the gradient descent. And so what's connection between them and why we call the gradient. And as I have talked several times, the gradient comes from the physical, and it means the reflection that it goes fastly, and it's just a word, and it is just a technical word with a real physical meaning. And so when we are trying to apply the charge boost, and we can have a meeting on the mathematics under the goose, and at that time we will just pay more attention on the math meaning of the gradient boosting. But today we'll just to focus on the inside of it rather than just the complex math formula, because the math formulas are way complexer, are way more complexer than the algorithms I put here. And so this is why today we just have a grasp on the inside of it, and this is enough for us to learn something about it. So compare with the ad boost, the most important thing for the gradient boosting algorithms is that it focused, or it just use the predictors to train on the residual errors made by the previous predictor. But when we are applying the ad boost, it will just focus on the training instances itself, and you will focus on the relative weight of the individual instance. But in the gradient boosting, the thing it care more is the residual errors, and this is how it works. And usually when we are talking about the GBRT, and it's a quite common word you will hear at other place, or it means that the gradient boosting regression trees, which means that it uses the trees as the base models, and also its job is to solve the problem of the regression. And this is where it comes from, GBRT. But actually, it's just one of the way we can use by gradient boosting. So today we'll focus on the gradient boosting, and after learning it, and you can use different ways to perform it. One of the common way is the GBRT, and when we just put them into a more extreme situation, and we will just call it charge boost, and this is what charge boost originate from. And the logic behind this is quite simple if we don't talk something about the mathematics, because the training steps it just repeating to train on the residues made by the current prediction, or the current result of the current result of the previous predictors and the real results we get from the data set. So on this picture, on this picture, the left column shows us the result of the individual decision tree models, and on the right columns it shows us the results of the aggregated ones we get from the example learning methods. So on the left side, for the in the top of this, you can see it. Actually, there is a set, or there are a set of data sets. There are a set of data, and we use the decision tree to make, or just to simulate the patterns. And this is the job of the regression. And literally, you can see it cannot just perform perfectly. It cannot perform perfectly as we want. So then we just calculate the residues. We use y minus by the results of this green line, and then we get a second, and then we get a second, we get a second data set, and we use the second decision tree to train on this training data set. And then you will just sum up all the results it will just sum up all the results of the individual decision trees, and then we will just repeat this process. So therefore, finally, we will just aggregate the 3 decision tree results, and we will just have the aggregated lines to just simulate their patterns. And as you can see, it will work well if we use gradient boosting to perform the job. Because when we are using an individual decision tree, the result will be like this. And the summations of 2 decision trees will work like this. And the summation of 3 will work stronger than the previous ones. And this is why we want to apply the gradient boosting. And there are 2 hyperparameters we should notice. The first one also will be the learning rate. So what's the physical meaning of the learning rate? And actually, it will just scale the contribution of each tree. And here comes from the regularization technique, and we call it shrinkage. And when we are talking about the regularization and what actually it refers to, and because it's just one strategy when we are dealing with the trade-off of the bias and the variance, because in like linear and polynomial regression meeting, we just talk something about what is the overfitting and what is underfitting, and what kind of algorithm will be prompt to perform overfitting than the other ones. And actually, you can see the more complex the algorithm is, the higher, like the higher the higher probability it will be to perform overfitting. Like if we are using the polynomial, and literally it will be prompt to be more overfitting than the linear regression. So this is why we need to use some regularization technique to prevent the result being such overfitting. And here's when we are set the learning rate value so low, and which means that we need more trees, and we need to increase the number of the, like here, the n estimators, and also the n estimator here. And which means that it will be more likely to just generalize better than the others. And here is the feature important it gives us. So the logic of this algorithm is quite simple, but the real mathematical knowledge will be more complex, than the previous one we learned from the adaptive boosting. And this is not the focus this is not the point we want to focus today. And usually we will have another technique to prevent the model being so overfitting. That is early stopping, and we have seen it in the linear and polynomial regression meeting also. And this is a common approach for us to use in various algorithms. And when we are using the DNN, maybe we will just use the early stopping also. And it's a quite useful way for us to deal with the overfitting problem here. So on the left side, you should know what is the warm start, and you should know and why it's important, because the warm start on the left side, it will help us to perform the early stopping methods. And here I just show an example on how to perform it when we are trying to use the gradient boosting. And so it's quite similar just to import like classifier. And if you want to perform the job of regression, and you can just import them the gradient boosting regressor, and it will work as well. So what is the early stopping? Because as we know, for the tree model, like when we are apply the random forest, and the more numbers we increase, the more numbers of the tree we increase, the more likely it will be to perform overfitting. And you can see as you increase the chaining trees, from the view of the training data set, it would be about to decrease the arrow. It would be about to decrease the arrows it gives us. Like maybe the arrow will represent the root mean square arrow, and it's quite a common one we see when we are do the regression job. And on the left side, we just perform a classification job, and we just select accuracy as the measurements. And so in this way, we will just find the maximum value of this rather than the lowest one. And this is one way for us to prevent from overfitting. So what is the charge boost? Actually, the charge boost will just be the extreme like the stage of it. And on the left side, I just make some practice on the charge boost. As you can see, we can use the charge boost because charge boost is as an independent library in Python work, and you can just import. You need to install them by using pipe-tree, and also you can import them from the sklearn library, but it is not recommended because it is work independently. So maybe the optimized one will be the one you import outlier. Like here, we use the early stopping technique. And here is the charge boost features important. And you can see clearly which feature will contribute more to the final result. And next time, when we are trying to use the charge boost and the light GBM, and we can schedule another meeting on it, and we will just focus on the charge boost and the light GBM. But today we just ignore them, and we just have some knowledge on what it looks like, and that's enough. And today we'll just go deeper, and the final one I want to introduce is the stacking ensemble learning method. So what is the stacking learning or ensemble learning methods? So despite of the two methods we applied before, so what are the ways we can use to perform the ensemble learning job, and is the one to just build up some match up, and this is what we call the stacking. And so what is the idea of the stacking? Actually, we train a new model to perform the aggregation rather than just to use some trivial functions to aggregate the results. Because when we are talking about the hot voting, we just to see what is the majority of the results or the predictors give us. But the other thing we can just think is that why don't we just use a model to do the machine learning job again, and maybe it will help us to just get the patterns of the the data set well, then by using some basic simple or some basic or basically simple techniques to do it. So at this time, the different thing is that we use a real machine learning model to perform the aggregation. So how can we use it? So when we are just construct two layers stacking example, we are just use when we are trying to build up the second layer, like two layers stacking example, the first thing for us to do is to divide the training set into two subsets. And we will use the first subset to train the predictor in the first layer. So what is the first layer? Because maybe we use this one, we use the random forest to perform the regression job here. And we use the SVM as the second one, and maybe we use the MLP as the third one. And so at this time, we use the first layer, or we use the first subset to train these three individual algorithms respectively. And then we get the result of it, because it's a regression job, and we will get a specific value finally. So we get three predictions value. And then we use the second subset to be the first layers, or like the testing set. And by this way, we are creating a new training data set. And because we use three estimators here, so the new training data set would be three-dimensional. And this target value is the label value we get initially when we import the data set. And by this way, as you can see, now we are creating a new training data set, and this new training data set would be used to train the blender. And what is the blender? The blender is the one we just call from outside, because we used a new model to perform the aggregation. And this new model is called blender. And it just mix up the results of the first layers. And logic is quite simple. After you use them, when you are trying to apply them into the real code, and you can just build up by this logic. And the thing you should pay attention to is that you need to divide the training set at the very first beginning because uh, the numbers of the layers you want to construct, and which means that the number of the subsets you need to create by splitting the training set. And this is the magic of the stacking ensemble learning method. And this is the whole this is what we need to learn today. And so it's the end of these lectures. And any questions on these three algorithms, just feel free to ask. Or any other else question on the machine learning, and is welcome to raise also.
So are there anybody to ask questions? And
Yes.
Chan just give three machine learning model. And the next model is just used to classification, right? Classify.
Yep. In the notebook, I just use the classifier to just because the data sets the Sany group give us is the classification job. So it's quite easy to perform the regression job because you just need to import the regressor, and then you can use the regressor to perform the regression job.
Okay. And Wumi just type the question in the chat, and you can see it.
Okay, I get it. So why did the trend set perform? So the result of the testing set is not satisfied, and maybe the problem is the quality of your training data set, because the more pure the training set is, and the more higher accuracy the model will perform. Because as we know, what is the machine learning algorithms? What is the real job of the machine learning algorithm to do is that it tries to make some it tries to extract some patterns from the real worlds and just transform them into some specific mathematical formulas. And so the data sets or the quality of the data set would guarantee the precision of the algorithm would give us. So if your testing set didn't give you the result you want, and maybe you can just resplit, or you can just resplit the whole data set, or maybe you just need to collect more data. You just need to collect more data, and you should guarantee that the data you want to train should be precise enough. And only this way you can guarantee that the result of your algorithm would be improved.
Okay, Umi, do you have questions?
Yeah, thank you, Sani. We are actually working on building up a better data set. Like we are collecting data still now, and also we'll make the imputation procedures correction. So I guess next time, again, when we apply the code, we'll see some progress.
Yeah.
Like,
And I just know that there are some other science group, they're just get started in the same problem as well. And they are trying to use some other algorithms to just refine their data set. And you can just consult whether there are some ways to help you to just pure your data. And because if there are some outliers, and it will just destroy your whole model. As I have showed the last meeting, when we are using the decision tree, if you just change the direction of the data set in the high dimensional space, and the final result will be totally different from the one you performed before. Because the tree model is quite sensitive. It's quite sensitive to the direction of the data set, and also it's quite sensitive to the scales of it. So if you just perform some normalization, and if you just change the magnitude of the data set, and the result will be totally different. So you are apart from the apart from collecting the data set, and you should care for some like the notice of some specific algorithms.
Okay, Turing and Sahu, do you have any questions?
No, I don't actually have any questions, but if you get time, actually I tried to do a run a simple regression model on a data set. It's there on Nerdstore. It would be really great if you could give me any insights on that. Like on your free time, anytime you can get back to me on Slack if it's fine.
Because the logic between them is literally the same. So when you are do the regression job, and maybe the only things for you to do is just to import them by using the regression, because almost the hyperparameters almost all the hyperparameters of the algorithms are the same when they are facing with the regression job, and when they are facing with the classification job. Maybe the difference is that the loss function, maybe the very least thing you need to care for is the loss function. But uh, actually, it's quite common for us to use the default loss function when we are using the algorithms which is not the deep learning algorithms. Because when we are dealing with the deep learning algorithms, and we need to care more on the loss function. But when we are use some other algorithms, we don't need to care much on it. And the quite usual for us to do is to use the common one loss function. And so it works as well when you are doing regression job, and you can just apply the thing I talked today when you are trying to solve some regression problem.
This code is stored at the GitHub.
Yeah, all the codes are put already in, or you can search them on the GitHub, but maybe they are not the optimized one because I just insert some new code into it, and after after this meeting, and I will just push them again, and you can just find these docs also in the GitHub.
Can you just send the GitHub link in the chat once, or in Slack, wherever you are comfortable with? I've lost
Okay.
that link.
Yeah. Sure.
Tan, you said that you will give an more introduction about the basic theory about the chat boost or other machine learning method in the meeting in maybe in the future. So I think
Yeah,
we can
sure.
so we can make a decision. So are there any questions about this method? Tejo, do you have any question?
I have no question. I'm still learning.
Okay, and thank you for chance sharing, and it's very great, and it will help. It's very helpful for us.
Okay. So could you just send me the record after this meeting? Because I need to upload them into the YouTube, and if there are some, if other groups want to use them, and I can just introduce them to see the record directly.
Yes, to him just record.
Yeah, no problem.
Okay. Okay, if we have any question, we will discuss at Slack. Okay.
Yes.
Thank you, everybody.
Thank you, Sany, and thank you now for organizing. Okay.
Wish
Thank you,
you
everyone.
guys a
Have a
good
great
day.
day.